So it turns out that these displays were not really adaptable to other settings or for evolving patient care. So which makes these highly customized displays really obsolete after a while. So we came up with this idea that seemed to fit with what we found in the literature and seemed to fit with where we're going. And then the idea was these small, modular graphical components that display trend information. And we called these widgets. So these widgets can be grouped and organized, such as heart rate, respiratory rate, and other data elements for a variety of different settings, users, and it's also scalable for evolving patient care. So this is a conceptual diagram of what was done and our expected outcome. So on the left hand is this electronic health record display. So the information is in various forms and formats and it's scattered throughout, so making sense of this type of display is difficult. So the first step was to see if we could group and prioritize this information. So you can see on the second screen, there's less information and it's grouped together. And then the second step was to see if we could widgetize and really optimize the display of these information components. And then finally, the third step was to integrate the group of these components together to see if this display could improve clinician performance. So the idea is that we would not only have these reusable components, but we can also validate these groups of components that could be placed into other displays, and all of this would maybe help lower some of these barriers to implementing graphical displays in different healthcare settings. So for this project, I'm going to introduce you to the first two steps and just a peek into the theories that we use for those. Then I'm going to delve a little bit deeper into that prototyping testing paper that we did for step 3. So back to our process. How can we group and prioritize this critical care information to enable this whole patient view? So we use chunking theory to give us a starting point. So chunking theory has roots in information processing and was first explored with chess players. So chunking is a process of grouping information into these meaningful wholes, which can increase our capacity to process information based on our working load, our working memory limitations. So the key insight from this theory that we applied to this analysis was that chunking was domain-specific, meaning that these chess players couldn't go into the radiology lab and start identifying tumors. And also that chunking depends on expertise. So experts can handle a lot larger chunks with more complex information. So since chunking is domain-specific and really depends on expertise, we recruited expert intensivists to sort these data elements into meaningful groups and then analyze these groups with a cluster analysis. So this is the paper that came out of this. So it's patient information organization in the intensive care setting, expert knowledge elicitation with card sorting methods. So the outcome of this was this concept map or hierarchy of data elements in groups. So we found that intensivists think about patients in terms of physiological systems, such as respiratory system, showing just a brief snippet of. But it's notable that the electronic health record doesn't store or present this information this way. It's similar to paper-based charts, so it's more source-based with medications and laboratory results. So now we know what information needs to be presented. We need to see if these widgets can now be used to display this type of information. So for this, we use the Gestalt theory for prototyping and testing these widgets. So a good Gestalt is this simple description of the visual stimulus. So basically the gist of the visual. So one of the main concepts is this pieces to parts. So a piece is this randomly cut piece of an image, whereas a part is a part of this whole if that whole actually makes sense. So to illustrate this idea, I've got this hexagon, which is plainly a whole shape. Now the second shape has 17 sides. The interpretation is that there are 2 rectangles. But we don't interpret this as a hexagon with additional shapes. So the idea is that we wanted to show these clinicians routinely measured data elements such as blood pressure in various forms and formats to see which had the most accurate interpretation of the data. So the outcome was this analysis, or this paper, an approach to critical care information display, designing modular graphical components for presenting trend information. So basically, we took a very broad and diverse set of prototypes and distilled them down to just a few optimized widgets. So I just gave you a peek into some of these theories and the first two steps of this process of prioritizing the information and refining the display. Now I'll delve a bit deeper into the results of integrating the widgets together and testing the prototype. So we thought, what is a common and complex task that requires pattern matching, and we can integrate these widgets to increase clinician performance? So we use this proximity compatibility principle, which is a group of theories, to see if we can group these widgets to identify circulatory shock. So the proximity compatibility group is this group of theories that links visual information processing with displays to tasks. And especially with complex tasks that require multiple data elements, an integrated information display can increase performance. So integrating information together can be done, for example, by how close the data is together, and also other visual channels, such as color, shape, boundaries, that may link this data together. So to give you a better idea of this integration in task, on the graph we have task performance on the y-axis and then task complexity on the x-axis. Then the dashed line is the highly integrated display, and the solid line is this unintegrated display. So for complex tasks, more information integration increases performance. But if the task is not complex, the integration is not needed, and actually unintegrated displays and more focusing on these discrete data increases performance. So according to this proximity compatibility principle, there's a spectrum for integrating data together, which means how easily can patterns be recognized among multiple data elements. So for example, a pie chart has low data integration, and it's good for processing these independent variables. Whereas E, or these object displays on the far right-hand side, are good for processing. They're very high integration, and they're good for processing multiple data elements. Now, our display is right in the BC area. So we sacrifice some of this data integration for flexibility, for different levels of tasks and complexity, and adaptability for changing healthcare environments. So what we need to prove now is that this type of display can now be used for complex tasks. So this is the paper, and this analysis is where we tested a group of widgets on this complex task. So impact of integrated graphical display on expert novice diagnostic performance in critical care. So identifying circulatory shock was our use case for this evaluation. And it ties into my father-in-law's case, and it's also a big concern for critical care providers as well. So nearly 1 in 3 patients will wind in critical care will wind up with circulatory shock, and it can increase mortality up to 80%. So circulatory shock is generally defined as a decreased blood flow and tissue perfusion, and is often formally diagnosed by hypotension and increased lactic acid. So early identification can help prevent organ damage and mortality. So these vigilant clinicians will search all over the electronic health record for signs and patterns that this may be happening, such as erratic vital signs, correlating trends that help them identify the circulatory shock. So there's a need for displays to help support clinicians in doing this task, such as recognizing, monitoring, and treating circulatory shock. So the research question was, can a display of widgets improve clinician performance on diagnosing circulatory shock? So we anticipated that this widget display would improve clinician accuracy and response time in diagnosing circulatory shock compared to a flow sheet or a conventional type display. We also anticipated that novices would have greater improvements with the widget display since they weren't quite as familiar with these flow sheet displays as well. So since chunking and information processing depends on expertise, we wanted to see if this integrated display that was already chunked and organized could help novices more. So this study was a within subject comparing different display types. So the integrated display consisted of these graphical widgets, and the conventional display was tabular, consisting of these discrete values. So we used mixed effects models to analyze the difference in outcomes between the two displays. And in the secondary analysis, we evaluated the display type by stratifying by expertise, so experts and novices. So we used 15 data elements for this, 4 physiologic and problem-based groups that included cardiovascular, respiratory, and infectious disease, and renal. And we got these from that first study where we identified the highest priority and grouping of these data elements. So this is a similar screen that the participants would use for this integrated display. So on the left-hand side are these tasks that we wanted them to complete, such as identifying shock and then selecting the shock etiology. And then on the right-hand side is this integrated group of widgets. Now there are several aspects of this display that increase data integration. So for example, the widgets are scaled to the same size. They also have the same 24-hour view. The top block of widgets were aligned in 2 columns with the most frequently used ones on top. And we also vertically aligned the widgets in the first column to help participants assess correlating trends and abnormal values at specific times. So the participant would advance this 24-hour window by 1-hour increments. And as these patient states would present, they would click on the corresponding task button. And for this scenario, this particular one was distributive shock, which typically presents with decreasing central venous pressure and systemic vascular resistance and increasing cardiac index. So for the conventional display, everything was the same, except we used a table of values for that display. So we analyzed 4 different outcomes: performance, latency, time, and etiology. So we define performance as the average of shock and no shock accuracy, meaning the proportion of correctly classified frames the patient was in shock and not in shock. And then latency was the delay of the frames from onset of shock to when the participant started identifying the shock. And then time was the number of minutes that it took the participant to complete that scenario. And then etiology is whether the participant correctly classified the type of shock that was shown in that scenario. So in total, we recruited 32 physicians from the University of Utah. And we balanced these experts and novices. Most of the experts were attendings in each of the ICUs, and almost all participants provided patient care more than 80% of the time. So these are the results. All right, so we have this integrated display here in blue. And what we found was that among all participants, performance significantly improved, meaning about 15% more of these frames were correctly classified with the widget display. And with etiology, or shock type, this was also significantly improved, meaning close to 20% more scenarios were correctly classified using this widget display. Now I know this is reversed. We have still a widget display in blue, but less is better. So latency among all participants was significantly improved was not significantly improved using this widget display. But the time it took to complete these scenarios was significantly better with the participants using this widget display. So with the exception of latency, the outcomes were significantly better using the widget display. So now when we stratified these results by experience, so experts and novices, there were some interesting findings as well. So we found that while experts seemed to improve using this widget display, only the novices had significantly improved. In fact, the novices' performance with the widget display was similar to the experts' performance using the flowsheet display. And for etiology, novices identified the type of shock 30% more using this widget display. And also novices using the integrated display had about the same etiology accuracy as the experts did using this conventional display. So I think the thing that's interesting and really adds face validity to these results is that the experts are used to looking at these flowsheet type displays to identify these patterns. These novices with the widget display perform nearly as well as the experts did with this flowsheet display. So I think his outcomes really demonstrate this nicely, the idea of potentially narrowing the gap between experts and novices through information display. So what does this all mean? So this means a few things. First, we were able to validate this proximity compatibility theory with an integrated display of widgets. So this was shown by faster and more accurate response time by participants using this widget display. Then second, this process of chunking information and refining this widget display may help compensate for undeveloped pattern matching skills among novices. And then finally, we demonstrated the effectiveness of a one widget set, but it's reasonable to think that these widgets could be regrouped with different tasks, and also additional data elements could be added as healthcare evolves. So the widget display may be this viable solution toward a wicked problem.